Over the last 35 years, thermal stress events have become increasingly severe on coral reefs. These events are associated with global climate change and have caused directional selection, removing the susceptible corals from many reefs. This has been linked to disease outbreaks among the corals, particularly in the Caribbean. Yet our understanding of coral disease is in its infancy. We know little about typical levels of disease prevalence in coral populations, and we know even less about disease incidence. As the oceans continue to warm, it is likely that the impact of coral diseases will continue to rise. It is therefore critical to understand coral epidemiology in the first step as potential remediation of coral disease outbreaks. The main types of diseases to affect corals are aspergillosis, which is a terrestrial fungus which enters the marine environment through stormwater runoff. It affects sea fans and sea whips and is widespread throughout the Caribbean. The fungus results in highly visible lesions as well as complete loss of tissue and skeleton. Black band disease is characterised by complete coral tissue degradation due to a pathogenic microbial consortium that appears as a dark migrating microbial mat. The microbial consortium consists of an assortment of photosynthetic and non-photosynthetic bacteria. White band disease is characterised by complete coral tissue degradation of Caribbean acropod corals. Only two species are affected, Acropora palmata and Acropora sevenosus. Unlike black band disease, this disease has no obvious microbial band, however is associated with a migrating line that moves across the colony.
So global warming is currently the greatest global threat to coral reef ecosystems. According to a NASA study, the average global temperature has risen by 0.8 degrees Celsius. This rise in temperature is having a detrimental effect upon coral reefs worldwide. One of the effects of global warming is the weakening of coral immune systems, as this can cause mass susceptibility to disease throughout coral populations. In a study appearing in the journal PLOS ONE, researchers at Ohio State University and their colleagues have demonstrated how the effects of climate change have destabilized different populations of coral microbes, opening the door for bad bacteria to overpopulate coral mucus and their bodies, causing disease to spread throughout coral populations. With an increase in temperature, there is a clear change in storm patterns with more frequent, stronger storms. These storms can be responsible for coral damage, with strong storms hammering coral reefs with strong storm surges. In Australia, the Great Barrier Reef has adapted to cope with the impact of cyclones and severe storms. However, it is predicted that intense cyclones such as Cyclone Hamish and Cyclone Yazzie will occur more often due to climate change. Reef recovery from such storms is slow because fewer corals survive to recolonise affected areas. An increase in severe cyclones could therefore contribute to the degradation of reef structures already weakened by coral bleaching and acidification. With a rise in storm events, there is an increase in surface runoff into the sea. With this is an elevated amount of nutrients, which are responsible for the increasing susceptibility of coral to infection, as well as the way the disease progresses. Increased levels of coral disease have also been observed following major flood events in Queensland over the past 5 years. These outbreaks often follow freshwater bleaching events that can occur and cause damage to inshore reefs. With an increase in temperature due to global warming, there is no instant solution. However, reducing other pressures on coral such as pollution and damaging fishing methods, this also may help with coral survival. Laws against coral destruction are also put in place to preserve remaining coral and prevent further damage. The UNFCCC, United Nations Framework Convention on Climate Change, is also put in place to combat against climate change by limiting global temperatures and the increase and coping with the impacts on climate change. That's all I've got.
According to National Ocean Service and United States Environmental Protection Agency, the pH is decreasing for over 200 years now, and this action is connected to humans' activity and industrial revolution, when the concentration of CO2 has been increased in the atmosphere and therefore is being more absorbed by ocean surface. The human's activity is affecting both Earth's climate and ocean chemistry, and it's reported that ocean pH has been decreased from 8.2 to 8.1 during the last 200 years. Scientists from the University of Queensland in 2008 have examined the impact of ocean acidification and come to the conclusion that the excess amount of CO2 being produced to the ocean causes such impact on coral reefs as coral bleaching or the loss of pigment. And together with this, ocean acidification slows down the productivity and growth of coral reefs. It may be caused because of making it more difficult to absorb calcium carbonate, which is needed for the growth of coral skeletons. Scientists all around the world are interested in protecting the diversity of existing coral reef systems. At the present time, coral reefs are being monitored by international organizations, including such Reef Resilience Network, Coral Reef Conservation Program, Coral Reef Alliance, and together with this, the ocean acidification is being monitored as well by, for example, UK Ocean Acidification Program, which aim to reduce the impact of humans' activity on the ocean and marine ecosystems.
At present, there are no known procedures for the prevention or treatment of coral diseases. As a result, the use of phage therapy has been investigated due to its previous uses in the treatment of human diseases. In a recent study, lytic bacteriophages were isolated for 2 bacterial pathogens that were responsible for coral diseases. By using these phages in a controlled aquarium experiments, it was demonstrated that each of these diseases could be controlled by the pathogen-specific phage. 9 corals were infected, 9 without. As you can see, the phage-treated corals had a greater percentage of healthy tissue than those without a phage. In each of the aquaria that did not receive phage, all 9 corals began to lyse after 14 days, and were completely devoid of tissue after 17. In the aquaria that contained phages, all corals remained healthy for at least 2 months.
In a separate experiment, corals were inoculated with V. coralliticus, and the specific phage remained healthy for 33 days, and then were re-inoculated with the pathogen. These corals remained healthy for an additional month, suggesting that sufficient phage remained associated with the coral tissue for at least 1 month to protect against second infection. The death of the corals after 27 days is most likely not the result of the infection because it is reported that the pathogen could not be isolated from these corals. The major advantages of phage therapy are host specificity, self-replication, and environmental safety. The phage only attacks and destroys a specific pathogen, multiplying rapidly at the expanse of its host bacterium, for more effective control of the pathogen. When the pathogen concentration decreases sufficiently, the phage will also decline. However, as phage therapies in the context of coral diseases are still experimental, conservationists need to respond to outbreaks to limit damage to the reef. At the Great Barrier Reef, researchers have identified reef-wide management strategies for mitigating disease impacts in 2 ways, by testing the effects of mitigating stress that could otherwise lengthen recovery times, such as water quality or physical impacts, and increasing understanding of the role of herbivory and predation by butterfly fishes on disease transmission. Creating these management strategies forms part of early warning systems to limit the substantial destruction of a key habitat to more than 25% of the ocean's marine life.